Okay. Hi, good evening. Am I audible properly? Hello, anyone?
Hello, good evening, sir.
Yeah, okay. Thanks. Okay, so let's wait few minutes, then we'll start. Okay, so today actually we'll be discussing some basic quantum mechanics after solving one question from 2019 paper, because there are no more questions left to solve. Like all the previous year questions has been solved. So in the next sessions we'll be discussing some particular topics, physical chemistry topics, which will be important for your GATE exam. Like in the next session I am planning to discuss the statistical thermodynamics topics. So we'll be discussing some important topics and solve some questions from those topics. If anyone actually wants me to discuss some specific topic, you can also suggest. Okay, so let's start for now, then we'll see. Let me just share my screen. Okay, so let's start. So this is question number 33 from 2019 paper, and the question says, suppose the wave function of a one-dimensional system is psi equal to sine kx and exponential 3i kx. So the form of the wave function of a one-dimensional system is given, and in an experiment measuring the momentum of the system, one of the expected outcome is. So we have to find out if we do or perform any particular measurement in an experiment, so what would be the one of the expected outcome of the momentum value. Okay, so the form of the psi is psi equal to we know that in quantum mechanics, in quantum mechanical sense, the momentum is an operator, right? So the operator form of the momentum is, so momentum P is the momentum operator. And the form of the P is minus h bar del x. So this is a one-dimensional system, so that's why P equal to minus h bar del x. So this is the particular form of the momentum operator. Now we know that the just if we operate momentum, this momentum operator on the wave function psi, then we will get some eigenvalue and we get back the wave function, particular form of the wave function psi. And in experimental measurement, the one of the outcomes corresponds to the eigenvalues, one of the eigenvalues. So one of the expected outcome means we have to just find out the what is the eigenvalue for this wave function psi with momentum operator P. Okay, so we have to just operate P on psi. That means minus h bar del x. Psi means sin kx exponential 3i kx. Okay, now minus, let's take the minus h bar common, then we have to just do the derivative with respect to x, right? So let's first take the derivative for this function, first function sin kx, keeping the exponential term constant. So it will be just k cos kx, right, times exponential 3i kx. Then this is the first term. Then the second term will be the keeping the sin kx term constant, and then taking the derivative of exponential term. Okay, so sin kx, then taking the derivative of exponential term with respect to x means it will be 3i k times exponential 3i kx, right? Okay, so the first term will be just minus I k h bar cos kx exponential 3i kx. Okay, and the second term will be minus, so 3, there is an I here and there is an I here, so I square 3i square k h bar sin kx times exponential 3i kx, right? So first term would be just minus I k h bar cos kx, then exponential 3i kx. Okay, then the second term will be just 3i square. I square means minus 1, so the negative and negative will be positive, so 3 k h bar sin kx, so it will be plus, then exponential 3i kx, right? Now about initial wave function was sin kx exponential 3i kx, but here you can see, so you can see that the derivative, after taking the derivative, we got the minus ikh bar cos kx times exponential 3 ikx plus 3kh bar sin kx times exponential 3i kx, right? Now there is some problem here, because to get the expected outcome we have to find the eigenvalue, but after taking the derivative, this wave function psi is not the eigenfunction of momentum operator p, right? Because if you operate p on wave function psi, we get this complicated function, so we are not getting back the this particular psi, right? Because if you just take the common exponential 3i kx here, then you will get 3kh bar sin kx minus I kh bar cos kx, right? So after operating p on or psi, we are getting this particular form of the waveform, this particular form. So this is not an eigenfunction, so this is not some value times our initial psi, right? This is not. So that's why we will not get any particular value of the momentum here. So the expected outcome will be the 0, because so this particular form will not corresponds to some value, let's say constant c times our initial psi, right? So because this is not our initial psi is not an eigenfunction of momentum operator p, okay? So that's why if we operate p or our psi on our psi, then we will get, let's say 0 times psi. So that means we will not get any particular value of the momentum, because this psi is not an eigenfunction of the momentum operator. So in experimental measurements, if we perform experiment on our system, so we will not get any particular value of the momentum. So 0 will be the answer. So okay, so this is the last question. So then let's okay, so any doubts from this question? You can just okay. So then today let's discuss some basic quantum mechanics, like okay, so we know that the quantum mechanics so we don't need to discuss fully, because we know that the quantum mechanics, the particular form of the wave function, so any properties, all the properties can be computed from the wave function of our system, right? So we know that. So we denote the wave function as psi. Now all the important properties or observable can be computed or can be extracted from this wave function psi. Now we know that the psi has to satisfy some criteria, right? Because psi has to be psi has to be continuous, psi has to be continuous, and there should not be any singularity of psi. So like this, so this wave function has to satisfy some criteria like continuous, singularity, and multi-valued, like this. So that means multi-valued means let's say for 1D system, our psi is a function of just one coordinate, let's say x. So if you just plot our psi x against x, so let's say our psi x look like this. Okay, that means for any particular value of x, let's say at this position, if we just take at this position, let's say x1, so at x1 the corresponding psi x will be, so at x1 the psi x1 have two possibilities, right? So this value, this value, this value, and this value, right? So it has two possibilities, two values. So this, so multi-valued means this. So at particular position x1, our wave function psi have two values. So this should not be the case. Psi has to be single valued function, and psi has to be continuous. Why continuous? Because we know that the Schrodinger equation is h psi equal to e psi, right? This is the time independent Schrodinger equation. So h is the Hamiltonian, right? Hamiltonian of our system. So h, classically Hamiltonian has the form of kinetic energy plus potential energy. So kinetic energy has the form of half of p square by 2m plus potential energy, some, let's say, Vx. So this is the classical Hamiltonian. Now in quantum mechanically, the Hamiltonian is an operator. So Hamiltonian operator for one-dimensional system will be just minus h bar square divided by 2m. M is the mass of our particle, then del 2 del h2 plus Vx, right, where x is an operator and the potential is also an operator. So this is the Hamiltonian operator for 1D system. So if you just operate h on our particular psi x, then we have to just take the double derivative with respect to psi x on psi x, right? So taking double derivative means psi has to be continuous. So if psi has a particular singularity, let's say if our psi look like this, so at this position there is a singularity here, right? Because there is so psi has infinite value, like let's say infinite value at this position. So we cannot take the derivative with respect to psi at this point, so that's why psi has to be continuous, and we need to perform the second derivative with respect to coordinate on psi, and psi has to be bounded because psi has to be normalizable, right? Because we know that the probability density, so what psi is the wave function, and probability density means probability of finding our particle at x. So probability of finding our particle at a particular position x, let's say. So the probability density will be, the particular form of the probability density is mod of psi square. So norm of psi square. So this is the form of the probability density. So in question, let's say you have the particular form of psi, and you need to take the you need to get the value of probability density at some point, let's say x equal to 0.01, some unit, arbitrary unit, let's say. So first you have to take the mod of psi square like this. This means psi x times psi star x. Okay, so this is the form of the probability density or mod of psi square. Then after getting this expression psi x times psi star x, then you can just put x equal to 0.01, then get the value of probability at that position x. Okay, now in principle, psi wave function, our wave function, system's wave function, is a complex function. Okay, that means it has some real part and some complex part, imaginary part. Okay, so psi x times psi star means psi, first you need to take the psi x function, and psi star means you have to take the complex conjugate of psi x. That means if let's say psi has our particular form exponential I kx, let's say this is our psi. So this is a complex function, right? Because I is a complex quantity, I equal to root over of -1 is in complex quantity, so psi x is a complex function, this function. Now psi star x means just you have to take I to -1, I to minus I, so minus I kx. Now if you just multiply psi x with the psi star x, you will get exponential I kx times exponential minus I kx, which should be 1. Okay, literally this will cancel. So mod of psi square for this wave function psi x will be 1. That means for any position value x, for any values of x equal to any value you can take, the probability density is going to be constant. Okay, so this is why it's called the plane wave. This is the expression of plane wave, where probability density is x independent, coordinate independent. Okay, so just remember this particular form, the probability density form. And psi star means you have to take the complex conjugate first, then you need to multiply with the psi x. Now in quantum classical mechanics or classical system, we know that we just use the variable x, p, position, momentum, like this. Okay, but in quantum mechanics, these variables has some particular form. This variables becomes operator and it has some particular form. Okay, so this is classical mechanics, and in quantum mechanics this will become the position operator, momentum operator, Hamiltonian operator, like this. So this operator has some particular form, and okay, I'll discuss later. And next, the commutation relationship. So in classical mechanics, we know that for any system we can get the value of position and momentum simultaneously with arbitrary precision. We know that, but we know in quantum mechanics the Heisenberg uncertainty principle exists. Okay, so in quantum mechanics we cannot get the position and momentum value for a particular system simultaneously with arbitrary precision, so due to the Heisenberg uncertainty principle. Okay, now the commutation relationship means, so any two operator, if you take let's say any two operators, let's say A and operator B. Okay, Now if you take this combination a b minus b times a, so this particular relationship has the particular form we denote it like this. Okay, so this is the commutation relationship between two operators a and b. Okay, now if the two operators a and b actually satisfy the commutation relationship, that means if a and b becomes 0, that means ab equal to ba. Okay, then we can get the simultaneous value of a and b with arbitrary precision. Okay, now we know if we just okay, so now let's, the position moment operator in quantum mechanics is just multiplied by position. Okay, let's say Vx, so let's say potential energy operator, which is a function of just x only, so it will be just multiplication of x by x. Now the momentum operator has particular form minus I h bar del x. Okay, now if you take the commutation relationship between these two operator, position and momentum, the commutation, this relationship will not become 0. So that there is a particular, the value of this commutation relationship will be just I h bar. Okay, so this is not 0 between the position and momentum. So that's why according to the Heisenberg uncertainty principle, we cannot get the position and momentum value simultaneously with arbitrary precision, because that is, this expression is not 0. Okay, and then okay, so this is the basic commutation relationship, and to get like any experimental quantities, all the observables like position, momentum, energy, angular momentum, spin, like any all the other etc. also. So all the observable quantities. So observable means if we perform an experiment on our system, then we can get the value of, or we can observe the value of position, momentum, angular momentum, spin, like this. Okay, so by performing experiment, we can get the value of position of our system, of our particle, momentum of our particle, energy of our system, like this. So that's why we call these observables. Now in quantum mechanics, let's say we need to find out the momentum value. So there is in quantum mechanics, so momentum is an operator, and let's say for one dimensional system in Cartesian space, it has the particular form minus I h bar del x. Okay, so and we also have some initial psi x, which is a function of x. So to get the value of momentum, so this psi x has to be an eigenfunction of momentum operator p. Okay, what do you mean by eigenfunction? So if we just operate p on psi x, so that means minus I h bar del x psi x, if we get, let's say, some constant c times psi x, this type of relationship, then we call it psi is an eigenfunction of momentum operator p. So this is an eigenfunction. So after operating with the particular operator on our initial wave function psi. If we get back our initial wave function psi with a particular constant value c, then we call it the psi is an eigenfunction. Psi is an eigenfunction of our constant value c. Psi eigenfunction of our moment operator, particular operator, and the constant value we are getting here, we call it the eigenvalue. Okay. Now if we, let's say if we just perform experiment on this system, one of the expected outcomes or one of the observable values we can observe is the eigenvalues itself. Okay, so eigenvalues are the values we will get if we perform experiment on this system psi, on this wave function psi. Okay, so this is the importance of eigenvalue, eigenfunction. Also, energy is also an operator like Hamiltonian operator. So if we just perform Hamiltonian operator, if we operate on psi x, we get back energy and get back this initial wave function psi. So then this is the time independent Schrodinger equation itself. So if an operator doesn't give if an operator doesn't give an eigenvalue, it is the eigenvalue 0. No, we cannot call it the eigenvalue 0 because we just, okay, yeah, if we just operate some a operator with wave function psi x, and let's say we get some expression psi prime x, not psi x. So we do not call the eigenvalue is 0, we call it the psi x. This particular psi is not an eigenfunction of this operator a. So that means, so I was also saying that I am going to say that this particular question has some problem, because here if we perform momentum operator on, if we operate momentum operator on this psi, we are not getting back the psi itself, and we are getting some complicated equation here, complicated equation. So so this particular psi is not an eigenfunction of momentum operator itself. So that's why we cannot get the values of eigenvalues. So I'm just a bit confused regarding this question, because we cannot get the eigenvalues here because psi is not an eigenfunction of momentum operator. So that's why I'm going to tell you, because if an operator's a, if we just operate a on particular wave function psi x and get some complicated expression psi prime x, let's say, not some constant times psi x, then we call it the psi x. This psi x is not an eigenfunction of operator a. Okay, it's not an eigenfunction, but the eigenvalue is not 0, because if, let's say, if we just operate a on psi x, then we get, let's say, 0. After operating a with psi x, let's say we get the expression, we get the value 0, then we call it 0 times psi x, right? So we can call it this psi x is an eigenfunction of operator a with eigenvalue 0. But in this case, we cannot call the eigenvalue 0 because the psi x is not an eigenfunction of operator a prime a. So this is the important, this is an important question. So eigenvalue will not be 0, so the function will not be an eigenfunction of operator, of that particular operator. Now there is some model system, important model system, like some particle in a box, particle in a 1D box, let's say. So in this model system, let's say it is 1D box, means one dimensional system, let's say, and the particle is confined between the 0 and L. Okay. Now there is an infinite barrier at position 0 and infinite barrier at position L, and the particle is confined in this region, and inside the potential Vx equal to 0. So this is the free particle, because it will not experience any particular force, because inside the potential is 0 and at the boundary potential is infinite. So particle cannot come outside this region. Okay, so at this position also Vx equal to infinite. So if you just solve H psi equal to E psi, right? So this is the time independent Schrodinger equation. H is the operator, has the particular form minus h bar square by 2m del 2 del x2 plus Vx, here Vx equal to 0, that means 0. Okay, just this kinetic energy term. So if you just solve this Schrodinger equation, you will get psi equal to some root over of 2 by L, then sine n pi L by n pi by Lx. Okay, you will get this particular form. Okay, now what is, so here L is the length of the box here. Now what is the n is the quantum number here. N is the quantum number, and it can get the value n equal to 1, 2, 3, like this. Okay, now the energy value will be, the available energy will be En n square h square by 8m L square. Okay, so this is the particular form of the energy value, after solving the time independent Schrodinger equation for this model system. Now here h is the Planck constant, you know, m is the mass of the particle, L is the length of the box. Okay, now so energy is discrete. So in quantum mechanics, so all the energy values are not possible. So there has some criteria depending upon the system. So some particular energy value will be possible. Okay, so this has to satisfy by the quantum number n. So for the particle in a box system, n will have 1, 2, 3, like this. So for n equal to 1, the ground energy state, ground energy, available energy will be just h square by 8m L square, right? For n equal to 2, it will be just 4h square by 8m L square. N equal to 3, it will be 9h square by 8m L square, like this. It will go on like this. So these are the possible energy states. So if you draw the energy diagram, so if you just increase the value of n, so energy will increase as n square. Okay, that means with the increasing value of n, the energy gap between two energy value, let's say En plus 1 minus En, this energy gap, this is the energy gap, will increase with the increase of quantum number n. So particle in a box energy diagram will actually look like this. So first this is the E1, let's say this is E2, let this is E3, this E4, let's say E5, like this. Okay, so this particular energy gap between two energy values is increasing. Okay, now so in the ground state, so this is E1, and also the one important thing is the ground wave function will have zero node. Node means where the psi probability density becomes 0. That means psi equal to 0. That means psi will change its phase from positive to negative or negative to positive. That position we will call it node. Let's say our wave function look like this. So this has 0 node because psi, this is wave function, let's say psi x. So psi x isn't changing its phase, but let's say our psi x look like this. So at this position, psi actually changing its phase from positive to negative. Let's say this is the positive side, so from positive to negative it is changing at this point. So at this point we call it node. So at this point psi x equal to 0, also the mod of psi square will also be equal to 0. That means the probability of finding the particle at this position will be 0. So this is the position of node. So at the ground state there will be 0 node. Then if we just increase the quantum number, the number of nodes will increase gradually. Like for first ground state it will be 0 node, first excited state it will be 1 node, second excited state it will be 2 nodes, like this. And for another very important system is 1D, let's say simple harmonic oscillator. Okay, now the simple harmonic oscillator means, let's say this. Okay, so Vx has the particular form of half of k x square. So this is, let's say, x, this is Vx, and this is the particular form, a whale type structure. Okay, then k is the force constant. So k will determine the stiffness of this whale. Okay, how steep is this or how broad is this will determine the value of k. So if the k value is large, that means the whale is very steep. Okay, if the k value is very small, force constant value is very small, then the whale is very broad, like this. The expression of k is 1/2 pi, no sorry, and there is a particular frequency of this oscillator, which is the omega. Let's say omega is the angular frequency. So omega, expression of omega will be omega equal to 1/2 pi root over of k upon mu. Okay, so this is an important expression. So omega is the angular frequency, k is the force constant, and mu is the reduced mass. Let's say molecule is AB. So what is the reduced mass? Mu AB will be Ma times Mb divided by Ma plus Mb. This is the expression to compute the reduced mass. Now let's get back to the Schrodinger. So if we just solve the Schrodinger equation for this system, so Hamiltonian operator will be just minus h square by 2m del 2 del x2 plus Vx. Okay, Vx has the form of this half k x square. So this is an important form, you need to just remember. Okay, so if you just solve this Schrodinger equation, you will get the energy value, possible energy value as n plus half h bar omega, or n plus half h bar means h over 2 pi, h bar means h over 2 pi, and omega means 2 pi nu. This is the angular frequency and nu is the simple frequency. Okay, nu has the unit hertz or second inverse, and omega is the angular frequency which has the unit of radian. Okay, so 2 pi will cancel, so you will get n plus half times h nu. So this is the energy expression for simple harmonic oscillator. Now let's say for n equal to 0 case, so it here n is also quantum number, and in simple harmonic oscillator, unlike the particle in a box system, n can have possible value 0 from starting from 0, 1, 2, 3, etc. Okay, now in particle in a box, n equal to 0 is not allowed, but in harmonic oscillator system, n can have value 0, 1, 2, 3 like this. So for n equal to 0, E0 have the energy half h nu. E1, n equal to 1, it will be just 3 by half, 3 by 2 h nu. E2 equal to 5 by 2 h nu. So it will continue like this. Now let's compute the energy gap. Energy gap means En plus 1 minus En. Okay, so it will be just En plus 3 by 2 h nu minus n plus half h nu. Okay, so n h nu will cancel, and 3 by 2 h nu minus half h nu, it will be just half h nu. Okay, so notice this. So for the simple harmonic oscillator system, the energy gap is just the half h nu. So it is independent on the quantum number n. It is very important. Independent on quantum number n. So if you increase or decrease the quantum number n, the energy gap between the two successive energy levels will be just the half of h nu. It will not change. So energy level H is the Planck constant. So energy level diagram for simple harmonic oscillator system will look like this. Sorry, let's potential will be just this. So it will be n equal to 0. This will be n equal to 1. This will be n equal to 2. N equal to 3 like this. So this energy gap between these two successive energy level will be just half of h nu. And how do you compute nu? Nu has the expression nu equal to 1 upon 2 pi root over of k by mu. So if you have the value of k, force constant, mu, reduced mass, then you can compute nu. Then you know the Planck constant value, h equal to 6.626 times 10 to the power minus 34 joule second. Then after computing nu, you can get the energy gap. Okay. So this is the quantum mechanical simple harmonic oscillator. So there are many problems also, but I think these are the important topics for the GATE chapters, because many of the questions comes from the simple harmonic oscillator system. So here the energy level has the form of n plus half h nu or h bar omega. And another important thing is to transfer units between the omega and nu. Omega is the angular frequency. Nu is only just frequency. That means it is it is second inverse or hertz. Okay. Now omega equal to 2 pi nu. Nu equal to c by lambda. c is the speed of light, lambda is the wavelength. Okay, now let's say if in one question if you have some frequency value in centimeter inverse unit, many of the spectroscopy question you will get that. So the frequency value, let's say 1000 centimeter inverse. Now centimeter inverse means it is not actually frequency, so it is an wave number. Okay, so wave number, which is, it's a nu bar, that means 1 upon lambda. So this has the unit of centimeter inverse or meter inverse depending on the situation SI unit. So this value is the wave number value of the wave number. Now how do you get the frequency value from this centimeter inverse wave number value? So we know nu equal to c by lambda. C times 1 upon lambda means wave number nu bar, so nu equal to c times nu bar. So nu equal to c times nu bar. So let's say c equal to, in CGS unit, 3 times 10 to the power 10 semi second inverse. Okay, and nu bar, let's say 1000, so 10 to the power cube semi inverse, right? Now this centimeter and centimeter inverse will cancel, so you will get, let's say 3 times 10 to the power 13 second inverse. So nu has the value now second inverse. So by this way you can compute frequency in second inverse from the wave number value which is in centimeter inverse. So this unit change is very important, and in many of the question you will see that you will get the value of frequency in centimeter inverse unit. Remember, you have to just convert the unit here, centimeter inverse to second inverse, to get the frequency nu. So you have to just multiply with the speed of light c. Okay. Okay, so these are some basic topics, and I think, and in the next class we will actually thoroughly discuss some important questions or some important topics from the statistical thermodynamics. Okay, it will be mainly just crash course type. Okay, so any doubts from this session, you can just ask. No, all clear? Okay, so remember, if psi after operating any operator on a particular wave function, if you do not get the initial wave function back with an eigenvalue, then we just call it that particular wave function is not an eigenoperator or eigenfunction of that particular operator, but the eigenvalue is not 0. So this is the important. Okay, so all clear or any doubts? Yeah. Okay, then I think I will just stop today's session, and we'll continue in the next session with the thermodynamics, statistical thermodynamics. Okay. Yes, no, anyone?
Okay, sir.
Okay, thanks. Then I will just signing off. Bye. See you in the next week.